Hello and welcome to another video lecture on basic concepts in organic chemistry, and today we will discuss delocalized chemical bonding. So let's get on with it. First we need to understand what is the difference between localized and delocalized chemical bonds. So localized bonds are those in which the bonding orbitals or the electrons are restricted between two atoms only. So you find bonds or you find orbitals or electrons which are restricted between two atoms, or you can say they are localized between two atoms. So such type of bonds are known as localized bonds. And molecules which have such type of bonds can be represented by only one Lewis structure. And examples of such type of molecules or bonds are sigma bonds and isolated double bonds. So if you have sigma bonds, they are localized. The electrons of a sigma bond are mostly localized between two atoms, and if you have an isolated double bond, then its pi electrons or even sigma electrons are also localized between the two atoms. Now, what are delocalized bonds? So as the name indicates, the electrons in such bonds are not restricted between two atoms, but they may be spread over three or more than three atoms. And molecules having such type of bonds cannot be represented by only one Lewis structure. So you can draw more than one Lewis structures for molecules which have delocalized bond, and sometimes we call them canonical structures. We will discuss that in detail in another instant when we will be discussing resonance. So canonical forms, or more than one canonical forms, can be drawn for molecules having delocalized chemical bonds. So let's see some examples of molecules having delocalized chemical bonds. So the first example is that of conjugated double bonds. Double bonds can be of three types: isolated, conjugated, or cumulative. Isolated double bonds are those which do not have any other double bond in the vicinity. Cumulative double bonds are those which are on adjacent carbon atoms, like in case of allenes. Conjugated double bonds are those which are separated by a single bond. So you have a double bond, then a single bond, and then another double bond. So it's like an alternate double and single bond system, and such type of system usually is known as a conjugated system. So molecules with conjugated system or conjugated double bonds have delocalized chemical bonds. A very famous example of such type of bonds is 1,3-butadiene. So let's see how the bonds in 1,3-butadiene may be delocalized. This is a molecule of 1,3-butadiene. You see a CH2 double bonded with a CH, then another CH, and then a double bond, and finally a CH2. So you can see that alternate double and single bond system. So when you have a two double bonds separated by a single bond, we say that the system is conjugated. So 1,3-butadiene has a conjugated double bond system. Now, the double bond or the pi electrons from this double bond can be delocalized over between these two carbon atoms, carbon number 2 and 3, and as a result, the pi electrons between these two carbon atoms are shifted towards this carbon atom. And as a result, we have this structure which is charged. And because of the shifting of these pi electrons between these two carbon atoms, this carbon here is left electron deficient. So now it has a positive charge, and we have a double bond between these two carbons now. And because these two electrons, the pi electrons, have been shifted onto this carbon atom, this now has a negative charge. Now, because this is unstable, when you have charges, these charges or the electrons can rearrange back to get back to this structure. So the negative charge of the two electrons on this carbon atom they are shifted back between these two carbon atoms, forming a double bond again, and as a result this pi bond or the pi electrons are shifted between these two carbons, so getting this carbon rid of the electron deficiency and giving this structure back. And you can see this double-headed arrow in between. When you see such an arrow, it's an arrow representing resonance. So this is a resonance phenomena happening between these two structures of 1,3-butadiene. Now we'll discuss resonance in detail in another video. You would think whether 1,3-butadiene exists in this form or it exists in this form. It neither exists in this form, neither in this form, but it exists as a resonance hybrid of these two forms, in which these pi electrons are spread over these 4 carbon atoms. So they are not localized between these two carbons or these two carbons, or even they are not localized between these two carbon atoms, but they are spread over all the 4 carbon atoms. And that also makes the bond length to deviate from a normal carbon-carbon single bond or a normal carbon-carbon double bond length. So if you find a carbon-carbon single bond here, but its bond length is slightly shorter than a normal carbon-carbon single bond because of some double bond character, because of this resonance. Similarly, the double bond between these two carbon atoms is slightly longer than a normal carbon-carbon double bond because of the single bond incorporated because of resonance. So this double-headed arrow shows the resonance phenomena. Now you would think, why we are shifting electrons in this direction? So you can shift the electrons in the other direction as well, because we have symmetrical molecules, so you can shift electrons. There are no electron donating or withdrawing groups, so you can shift the electrons in either direction. And so as a result, now we have a negative charge here and a positive charge here, which can then go back and give you the first structure. Now we have this structure. This is actually the same structure, which is the neutral form of 1,3-butadiene, and as a result of the shifting of electronic density, we get these charged molecules, and we call them the charge separated structures of 1,3-butadiene. When you have a neutral and a charge separated structure of the same molecule, always remember that the neutral molecule will be more stable as compared to the charge separated structure. So the molecule never happens to be in this form or in this form, but it actually is a resonance hybrid of these two forms. Now let's see how the molecular orbitals of 1,3-butadiene would look like. Because of this resonance, let's see what molecular orbitals are formed and how they would look like. So this is the structure of 1,3-butadiene, and let's see these orbitals, these molecular orbitals, or which we also call the frontier molecular orbitals in some cases, on an energy scale. So the first orbital, the molecular orbital that is formed, is looks like this. So you see this white sigma bond network that shows the 4 carbon atoms, the sigma bonds between 4 carbon atoms, and then we have these p orbitals forming the pi bond. So you have 2 pi bonds here, so the pi bond is formed between these 2 orbitals and these 2 orbitals. Now in the first molecular orbital, the electronic density is easily shifted or spread over all the carbon atoms, all the 4 carbon atoms. In the second orbital that could be formed in 1,3-butadiene, we have a nodal plane right in the center of the molecule. You see this red dot here, this is the nodal plane. Remember that the wave functions of orbitals across the nodal plane are opposite. You see here, the shaded part of all the orbitals is above this sigma framework, and the unshaded part is below the sigma framework. But here if you see, these 2 orbitals have the shaded part above this sigma network, but after the node, the shaded part is down below the sigma framework. And when you have opposite wave functions of two orbitals, they cannot overlap or they cannot share their electronic density. Now why we have this nodal plane here, that again I'll discuss later in another video in more detail, where and how many nodal planes you can draw in a molecule between the molecular orbitals. So in the second molecular orbitals, electronic density can be shared between these two orbitals and these two orbitals. Remember, when you do not have a nodal plane between the orbitals, their wave functions would be similar on both sides of the carbon sigma bond, right? So you see this unshaded part above here because we have a shaded part here and a node, so the unshaded part should be above, and because we don't have a node here, so you draw the unshaded part above the sigma bond and the shaded part is right below here. Now in the third molecular orbital we would have two nodes, one here, one here. So the first one has a shaded part above, then we have a node, so the unshaded part would be above the sigma framework and the shaded part would be below. Then we do not have any node, so these two would have the same wave functions above and below, and then we have a node, so these two would have opposite wave functions above and below the sigma framework. So only these two orbitals can share electronic density. And finally we have a molecular orbital having three nodes, and so you see that the wave functions of all the orbitals are opposite on adjacent carbon atoms. So there is no sharing of electronic density possible in this molecular orbital. And as you can see that they are drawn on an energy scale, so this one has the lowest energy, this one has the highest energy, and in quantum mechanics we call them as psi 1, psi 2, psi 3 and psi 4 orbitals. Now these molecular orbitals will accommodate all the electrons involved in this delocalization. And so because we have four molecular orbitals, and you already know that you can fill only two electrons in one molecular orbital, and you always start filling from the lowest energy orbital. So the first two electrons go into the psi 1 and we are left behind with two more electrons. Why only two? Because we are only concerned with the pi electrons. Remember, the sigma electrons are not involved in delocalization here. Only the pi electrons are involved in delocalization here, and these orbitals only mention the orbitals involved in delocalization. So they do not have anything to do with the sigma bonds. They are only the pi electrons involved in delocalization, or the molecular orbitals formed after delocalization of the pi electrons. So we have four pi electrons. The first two go into the psi 1 and the second go into the psi 2 orbital. The third and the fourth, psi 3 and psi 4, are empty. Now the first two are the bonding molecular orbitals. So you already know from the molecular orbital theory that the number of bonding molecular orbitals are always equal to the number of anti-bonding molecular orbitals. So we have four molecular orbitals here. The first two are the bonding molecular orbitals, and because you have two bonding, so you must have two anti-bonding molecular orbitals which are empty. And because all the electrons are in bonding molecular orbital, this molecule is quite stable. Let's see another example in which the double bonds are in conjugation with an adjacent p orbital. Adjacent p orbital means that a p orbital on an adjacent carbon atom, and that adjacent p orbital could be empty, it could be filled, or it could be half filled. So as an example, we could have propenyl cation, propenyl anion, or propenyl radical. So if the adjacent p orbital is empty, we have a propenyl cation. So we have a carbon-carbon double bond, and on adjacent carbon we have an empty p orbital. And when you have such a case, these pi electrons between these two carbon atoms can be shared or transferred to between these two carbon atoms to give you this structure, and these pi electrons then come back as a result of resonance to give you this. So they are interconvertible through the resonance phenomena. Remember, this is not equilibrium between two different structures. It is the same structure and the molecule resonates between these two structures. And again, there are no true single or double bonds. The bond lengths are longer than the double bonds and shorter than the carbon-carbon single bonds. Now, if the adjacent p orbital is filled, so we can have a propenyl anion, and you can see now that the electrons from the anion are shifted between these two carbon atoms, and as a result these pi electrons are shifted onto this carbon atom, and we get this structure in which we have an anion now on this carbon or a negative charge here, which can shift back to give you this structure. Just look at the direction of the arrows or the shifting of electrons. Here the electrons are shifted towards a positive charge, and that is logical because a positive charge would attract electronic density. But here the electrons are shifting away from a negative charge, means this negative charge has to get, this carbon atom has to get rid of the negative charge, and that is to share these two electrons between these two carbon atoms. It gets rid of the negative charge and gains stability. So this negative charge and positive charge, it resonates between the first and the third carbon atom to give some sort of stability to the system, and does not allow the positive or the negative charge to accumulate on only one carbon atom. So delocalization as a whole brings stability to the system or to the molecule. Now we can have a p orbital that is half filled, so that is a case of radical. So when you have a radical catalyzed mechanism, you don't draw this full-headed arrow which shows the shifting of two electrons, but you draw a half-headed arrow or a fishhook arrow to show the shifting of only one electron. So the presence of this one electron here is unstable or brings instability to the system. So this carbon would like to find some partner for this electron, and that partner comes from this pi bond. So one electron from the pi bond comes here, and this electron, the unpaired electron from the radical, comes here to form a double bond here between these two carbon atoms, and the second electron of this pi bond is shifted then towards this carbon atom, forming a radical now at this carbon, right, which can then shift back again through a single electron transfer to get back to this structure. So again, this single electron resonates between the first and the third carbon, and the two structures resonate between each other. Now let's discuss their molecular orbitals. So let's see them on an energy scale. First, for the propenyl cation. Remember, we have three orbitals now. The two orbitals of the double bond shown with the pink color, and one p orbital shown with the green color here. So when we have three orbitals mixing together or joining together or bonding together, as a result we would have three molecular orbitals formed. So in the previous case we had 4 pi orbitals involved in resonance. So as a result 4 molecular orbitals were formed for 1,3-butadiene, but in this case only 3 orbitals, 1, 2 and 3 orbitals are involved in resonance or delocalization. So 3 molecular orbitals would be formed. This is the first one in which there is no node, and you can see that the shaded part of all the 3 orbitals are above the sigma framework. The unshaded part is below the sigma framework, and when you have similar wave functions of the orbitals, they can effectively overlap or share electronic density. The second one, of course, will have one nodal plane right in the center of the molecule. So this orbital no more is visible because it's a node, and remember, nodal plane or node is an area where you do not find any electronic density. So when you don't have any electronic density, you don't have an orbital. And across the node, of course, these orbitals will have opposite wave functions, and so they cannot share electronic density or they cannot overlap to share electrons between them. And then we have another orbital having two nodes now, and so across the nodes again these orbitals will have opposite wave functions, so no resonance is possible here. Again, we can call them as psi1, psi2 and psi3, and you can fill in the electrons as well. Remember how many electrons are involved in resonance or delocalization here? Only two of these carbon-carbon double bond. This p orbital is empty. It is involved in resonance or delocalization, but only two electrons are involved in this process, and those two electrons will go into the lowest energy orbital, that is psi1. Now we have three orbitals, and as you know that we can have equal number of bonding and anti-bonding orbitals. So if this is the bonding orbital, this would be the anti-bonding orbital, and so we have a non-bonding orbital in the center now. So this is a non-bonding orbital, and we have a lowest energy bonding and a highest energy anti-bonding orbital for the propenyl cation. Now let's see the molecular orbitals for a propenyl anion. Again, we have a carbon-carbon double bond now in delocalization with an anion. So again, we will have 1, 2 and 3 orbitals mixing together or involved in delocalization to give rise to 3 molecular orbitals again, and they will look exactly similar to those of propenyl cation as we discussed earlier. So we do not have any node here, we have one node and we have two nodes in the third orbital, and we call them as psi1, psi2 and psi3. And now to fill them, how many electrons are involved in delocalization? 2 of the double bond and 2 in this filled p orbital. So we fill the first 2 in the psi1 and the last 2 in the psi2. Again, they are the bonding, anti-bonding and the non-bonding orbital. So the last electrons go into the non-bonding orbital in case of propenyl anion. For a propenyl radical, again we have 3 orbitals involved in delocalization, 2 of the double bond and 1 p orbital on the adjacent carbon atom. So again we will have 3 molecular orbitals, psi1, psi2 and psi3, and to fill them now we have 3 electrons, 2 of the double bond and 1 unpaired electron on the adjacent p orbital. So we fill the first 2 here and the remaining 1 electron is filled in the non-bonding orbital. So the orbitals look exactly similar to as in the first 2 cases, but the number of electrons are different in all the 3 cases. The third example is a double bond in conjugation with the lone pair on an adjacent atom. So lone pairs are usually found on heteroatoms like oxygen, nitrogen and halogens. So we can have such type of delocalization in case of enols, enol ethers, vinyl halides or enamine. So let's see how it would look like. So if we have an enol, a double bond and an OH attached to it, so you see that we have a carbon-carbon double bond which is in conjugation with the lone pair on adjacent atom. This lone pair could be delocalized over and shared between carbon and oxygen here, and as a result these 2 pi electrons are shifted onto this carbon atom, forming a negative charge here. And when you have oxygen forming 3 bonds now, it will have a positive charge because it has formed an extra bond at the expense of one of its lone pairs. So it has a positive charge now and it is unstable in this form. So to gain stability again, it attracts this pi electron density towards itself, and as a result the negative charge again is shared between these 2 carbon atoms. So we have a double bond again and a single bond, and the lone pairs on oxygen are also restored. So the structure again resonates between these 2 forms in case of enols. Enols can also form ethers. So if we have an OR instead of OH in conjugation with a double bond, the resonance looks exactly similar to as in enol, and we have a positive charge on oxygen in one instance in the charge separated structure, and in the neutral we do not have any charges. The same is observed in case of enamine. So we have a double bond on between two carbons, and then we have a nitrogen having a lone pair which can again be delocalized as in case of oxygen in these two cases, and we have a positive charge on nitrogen and a negative charge on carbon, which is then delocalized again or resonate again to get back to this neutral structure in case of enamines. And finally, we can have such type of delocalization in vinyl halides as well, right? So let's see their molecular orbitals. Again, we have the two orbitals of the pi bond and another orbital that has the lone pair. So we have three orbitals, and as a result, three molecular orbitals would be formed again. So we have to fill in the electrons now. So how many electrons are there? Now in all the 3 or 4 cases, we have 4 electrons. 2 from the carbon-carbon double bond and 2 from the lone pair. So we have the last electrons filling up the non-bonding orbitals of enols, enol ethers, enamines, or vinyl halides. These are some of the cases in which you can find delocalized chemical bonds. These are not the only cases. We will discuss in more detail delocalization in case of benzene, and we will discuss its molecular orbitals in more detail in a separate video lecture. I hope it helped you. Stay tuned for more lectures in delocalized chemical bonds, resonance, and basic concepts in organic chemistry. Thank you so much for watching.